Hello, everyone. Thank you so much for joining us today. I hope everyone is doing well. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all to our webinar today entitled Technological Challenges in Deep Sea Mining. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. So with that, I'm very happy to introduce our speaker today, Frank Lim. Frank is currently an advisor to 2H after stepping down as Global Director in 2017. He started his offshore engineering career in 1983 upon completing his PhD in mechanical engineering and has been involved in deepwater projects all over the world. He has led all of the 2H projects in deep sea mining since 2007 in providing design consultancy of the vertical transport system to major stakeholders in the industry, which is still in its infancy. So with that, I'm going to pass things over to Frank to get us started today.
Hello, everyone. Wherever you are, good morning, good afternoon, or good evening. As Victoria had very kindly introduced me, so I don't have to say any more about myself. I'm going to start today by talking about deep sea mining, the technological challenges, and I'm going to speak very simply, for the non-experts, because I think there may be people who listen in who are interested to know what deep sea mining is about. So I just want to do a very general introduction and cover the main components in the deep sea mining system, the design challenges that we face in getting them ready. Now, because 2H Offshore is a deepwater riser design company, so naturally I have this special affection for the riser system. So I'm going to talk a little bit more about the vertical transport system, and then I will cover the deepwater issues, and then draw some conclusions. Yeah. Okay, what is being mined? Broadly speaking, there are two types, and one is what we call on the left. You can see my cursor. Yeah, okay, on the left, seafloor manganese nodules. In short, is SMNN. Yeah. And then on the right is the seafloor massive sulfides, SMS in short. And I'll explain that manganese nodules, that's what a lot of people know about. They are really just crystallized polymetallic nodules scattered on the seabed. You can see the egg shape or size of a fist, nodules scattered all over the seafloor in certain parts of the world. We can harvest them by scraping on the seabed. It's a bit like mowing the lawn. So it's a very fast process and a very large coverage area in order to meet the production and economic target. The other type is, as I said, seafloor massive sulfides, SMS. They are really extinct seabed volcanoes. You would have seen videos or pictures of smokers' chimneys, that you see in some nature programs. They are the one that is still blowing smoke. They are active. But here we are really talking about the extinct one, the dead ones. We don't touch the live ones. These are surface deep. They are 1 or 2 meter deep on the seabed, and the recovery process requires excavation and crushing of these rocks. Yeah? It's a very slow process, and the area you cover is quite small. Right, where are these resources? They're all over the world if you care to look. Some in exclusive economic zones, EEZ. These are the areas 200 nautical miles from shore of a country that the country has exclusive right for exploiting the resources. Yeah. So, but majority is in international water outside the exclusive economic zones, because the world, nearly 2/3 of the world is covered in ocean, and only a very small part of it is close to shore. The rest is in international waters. Yeah. Now, there's an organization called International Seabed Authority, ISA. It's a United Nations organization that is headquartered in Jamaica. It regulates and manages the manages the mineral resources in the international waters. So I want to briefly talk about examples of resources in EEZ. Yeah? And this is quite a well-known example in Papua New Guinea. What they are mining are SMS, the extinct volcanoes. The first commercial attempt of deep sea mining by Nautilus Mineral, a Canadian company, but they're based in Brisbane, Australia. But the project is now suspended because of lack of investments or running out of funds to get to the actual operational stage. But you can see on the right, you see the mining scheme that they have, a mining vessel with a riser hanging below it, and a pump. Yeah, and I'll explain that a little bit more. And then an example of resources in international waters. The most famous one is this place called Clarion-Clipperton Zone. Is out in the middle of nowhere between Hawaii and Mexico in the Pacific Ocean. And this is the manganese nodules, the nodules that you saw scattered around on the seabed. And it's a very large area, 6 million square kilometers in 4,000 to 6,000 meter water depth between and ISA, because it's managed by ISA, many exploration licenses are already issued, and some pilot production trials have started. Okay, this is a general mining configuration. The main components, what we have is the mining platform, the production vessel, which will also process the ore, and then it will be transferred to an ore transport vessel that bring the ore to shore for further processing. Now, below the mining platform is a vertical transport system, VTS, and here is a hanging version, and then it's got pumps along the riser to pump the slurry from the mining tool that is scraping the seabed or excavating, and then the ore they're mixed with water and get pumped up the vertical transport system to the platform. And typically you see a flexible hose that connects the crawler or the mining tool to the pumps so that the crawler, the mining tool can move around freely on the seabed, yeah, and with the vessel possibly following it. Now, here you see hanging from here is the disposal of wastewater, because the ore goes up in a mixture of solid and water. You need to separate the water out and discharge it back, to somewhere closer to seabed, because you can't just dump it over the vessel, because it will just pollute the surface water and kill the marine life. Yeah. So it has to be returned. Wastewater has to be returned to close to the seabed where it comes from. Okay, I will talk briefly about each major component. First one is the production vessel. This is the Nautilus example. It's got quite a number of A-frames, you can see here, and a tower for deploying the riser. The A-frames are to deploy the miners, the crawlers, yeah, to the seabed. Now, the number one challenge of the function of the production vessel is dewatering of the slurry. Yeah? Now, the slurry typically consists of 85 to 90% water, 10 to 15% solid ore. Yeah? So it's a lot of water. And this is water from the seabed, which is colder, it's got different chemical composition, and you can't just dump overboard, as I said. So you need to dispose it, wastewater disposal, get rid of it safely, cleanly. And you have to store the ore, the watered ore, which is still moist, and have then got to transfer this ore to the vessel that go back to shore. Now, the vessel designer tells me that the ore is wet and then stored, and then you need to dig it back up to transfer to the transport vessel is as challenging as try to bring it up from the seabed, because when it consolidate, then it's difficult to dig it back up again. And now the easiest way to transfer something is to have mixed with water, because solid doesn't flow easily. Now you've just got rid of the water, and now you've got to put the water back. It's a bit of a contradiction, so it's a bit of a headache. Yeah. Now this vessels or this production vessel is out in the middle of nowhere, as in the Clarion-Clipperton zone. So you need to have fuel supply to keep the power going, engine running, the crawler pump, and all working away. So you have this fuel supply and power generation, logistic supply issues. When you are out in the middle of nowhere, there's no infrastructure at the moment. And then the crew and living logistics, flying people in and out. Now, for the Nautilus example, you have this riser storage and deployment issue. That you need a derrick, and then you need a pipe storage area, and then you need to have launch and recovery and maintenance, of the crawler and the pumps facilities all on board. So I'm sure there's more to it. I'm not a vessel expert, so I'll move on quickly to other things. Crawler. The crawler technology is adapted from seabed dredging and trenching. You see, this is an example of this is the Nautilus crawlers, the three of them, because in Nautilus they are mining SMS, the seabed volcano. It needs a lot of digging and crunching and sorting out before the ore is mixed with water to send up the riser. And now being so deep, now Nautilus is about 1,500 to 3,000 meter water depth, to 1,500 to 2,000 meter water depth, and it has very high external hydrostatic pressure, which the components of this crawler have to withstand, and they have to be launched and recovered for maintenance, on quite regular intervals, and they have to move around the seabed in a pattern, to very efficiently, leaving no stone unturned, so to speak, to get the most out of the seabed. Power consumptions, as you can see, they are massive and will require a lot of power to keep it going. Maintenance, every few weeks or less, you will have to bring each of them up for making sure that the parts are still functioning efficiently. Cable umbilical management. You can see in the last picture that you see the crawlers are all working simultaneously. One digging, one sorting, and then one crushing to get it up the risers. So you see the cables that are used to deploy them have to be managed so that they don't get entangled. Yeah? Then traction on the soft seabed. You need to be heavy enough to track, not light enough to skate along. Yeah. So there's a bit of a fine balance between how heavy these machines can be. Minimize plume generation. This is a very environmental concern. Is that when you're digging, it generates plumes that get washed by the seabed current, to far distance away. So there are a lot of research now going on in trying to minimize plume generation, try to suppress the plume at source, so as not to let the plume go too far away. And then there's of course synchronization of vessel and crawler movements. The vessel may have to move along. So then we come to the vertical transport system, which is my subject really. The technology is derived from seabed dredging and oil and gas drilling industries. So this is a generic layout, mining vessel, a tower, and then a riser, hanging, and jumper, and a crawler. And here what you see is not just a pipe, but also an umbilical that powers the pump. Yeah? So there's pump, riser pipe string, and the jumper hose. And I'll describe them in turn. Pump. This picture here is courtesy of GE, or previously Hydril. They had a pump design for drilling, deep sea drilling, and it was converted for seabed mining, because in drilling it was handling drilling mud. Here is dealing with slurry, from the miners. So it consists of these chambers. These are bladders, that collapse and expand, and work as like a piston, to squeeze the flow from one chamber to another, and then out from the last one into the riser. So this pump hangs directly below the riser and hovers over the seabed. And for a positive displacement pump, it can create very high pressure difference. So one pump with 10 chambers is able to pump the slurry up, say, around 2,000 meters of risers to the surface. But the flow rate is low, and because it's a piston effect, it's a pulsating flow, and we require multiple chambers, as in this case, and tuning to smooth out the pulsations. It's located at the bottom of the riser string, and the good thing with this on Nautilus was that instead of electrically powered, we are using wastewater that is separated from the slurry. We use surface pumps to pump this wastewater down to these chambers to drive the pumps, to drive the chambers, and so it kills two birds with one stone. We're able to drive the pumps, and we are able to discharge the wastewater back to the seabed. And the only electrical requirement is to synchronize, the movement of the chambers, and so it's quite small comparing with having to drive the chambers directly with electrical cable. With a pump like this, you should be able to disconnect it, put it on the seabed, and recover the pump separately for maintenance, and not having to retrieve the riser. The other alternative to positive distillation pump is centrifugal pumps. Here, it's courtesy of IHC. Here, what you see is a pump station with two centrifugal pumps in it. So you need several of these centrifugal pumps in a riser string to relay the slurry from the seabed to the surface. It is because the centrifugal pumps can create quite low, relatively low pressure difference. So you need many of this, to give you the total pressure required to bring it to overcome the hydrostatic heads. The good thing is that the flow rate is very high. It's a continuous flow because it's centrifugal, rotation, and it's located at multiple locations. In the study we did for 5,000 meters water depth to pumps manganese nodules, in 5,000 meter water depth, we need 6 pump stations, 6 of these things. The thing is that to avoid retrieving the risers, each time you need to maintain the pumps, we would suggest that you could do some mid-water maintenance and repair. But I was told that these pumps are very reliable and don't need very much maintenance from their experience in dredging. Pipes, that's a long pipe string, and first thing comes into most people's mind is unbonded flexible pipe. And here you can see a picture of it, a cross-section of it, typical cross-section of it. It is very compliant. You can install it by reeling and unreeling from a drum on this reel vessel, as you see. It's continuous construction, and it's not fatigue sensitive. But it's got water depth and diameter limitations. You can't. But for mining, the pressure is small. The internal pressure is relatively small compared to oil and gas. But nevertheless, there's still external hydrostatic pressure to design for. Issue with this is it's got a sheath that is quite susceptible to mechanical damage, and once it's cut, then seawater gets into it and it can corrode the armor wire and making it lose its tension capacity and fatigue. And it's quite expensive. Flexible pipe is very expensive and quite heavy too. Another option is thermoplastic composite pipe. Again, it can be real, but it is you require a larger diameter drum than the flexible pipe option you saw earlier. It's stiffer than the flexible pipe. Again, also good thing is non-fatigue non-fatigue sensitive. You need a larger reel because of stiffer pipe. Now, at the moment, there's a severe diameter limitation. 8-inch at the moment. That's what the TCP pipes manufacturers are doing at the moment, maximum. There are 2 TCP suppliers. To convince them to do larger diameter, they will have to have a good business case. And then we have bonded hose. This is built in short sections and connected together with a big flange like here. Problem is that they lack tensile strength, and there's a pressure limitation too. The end fitting is quite weak, but it's suitable for short jumpers. Yeah, the curvy jumper that you see connecting from the bottom of the riser string to the crawler. Yeah, and in fact that is what is used for Nautilus, or would be used for Nautilus. Then come back to the old-fashioned steel pipes. This is very well established technology, extensive knowledge and experience, and good track record in deep water drilling. We can do up to large diameters. Like drilling riser is typically 21-inch, so this is a lot more than the typically 14-inch that we need for mining. You require mechanical connections, insulation from derrick. They are about 75 foot long, 23 meter section each. Now steel get worn out by the flow of slurry up the wall, so you need a wear liner, and welding quality is critical in order to have good fatigue resistance. Deep water challenge, we're talking about 2,000, 4,000, 5,000, kind of water depth. And then drilling, most drilling facilities are designed for 3,000 meters. So now for mining, we are going even deeper. Yeah. So high riser payload, because when you hang it, the vessel has to support the riser weight. You need large deck space for storing riser components, long time to deploy and retrieve riser. And the thing with very deep water is that there's the ocean conditions are uncertain. You would see current going in different directions, along the way down, and it's quite unpredictable. I'll talk about VIV, vortex-induced vibration, later. That causes component fatigue, and you need contingency measures for such deep water application. VIV, vortex-induced vibration, as you can see, is vortices form alternatively behind a cylindrical body in a current flow. Yeah, and the alternating vortices can generate vibration in the pipe, quite high frequency stress reversal that will eventually can fatigue the riser if you don't manage it properly. We could mitigate VIV fatigue. That means it's just not the current. Yeah, it's not just current. When you move the vessel, carrying the riser with it, the vessel towing speed is in itself a flow speed. Yeah, and you have to move slowly in order not to generate too much VIV, but that can mean not meeting the production target and not covering large enough area. Yeah, so you could consider suppression strakes like shown in the picture here, but generally we would like to discourage it because it complex, is quite difficult to install, and increase system drag and vessel fuel consumption. And connectors all need to be fatigue resistant, and you need special joint at pump connection to reduce local bending stresses. We could introduce in-place monitoring and tracking of fatigue damage to know how much damage is actually accumulated, and we could swap them around and try to avoid damage in that way. Yeah. Or we use riser pipe with high structural damping or fatigue resistance, like flexible or TCP. Special issue for ultra deep waters. Here we're talking about ultra deep now, yeah? Because the riser pipe is kind of slender, and in a very long string, yeah, it becomes a spring, yeah? A very soft spring with a mass like the pump hanging below it, and then you've got wave, popping the vessel up and down, and it generate axial excitation. When the spring stiffness gives you a axial natural frequency that is close to the wave frequency, then you can have a axial resonance problem. When the riser is mining, at a known depth, known water depth, you could put in a damper and a system to reduce the resonance. But during deployment, the length of the riser is increasing, and you're bound to come across a length that gives you the natural period of the waves. Yeah, and so during deployment, we will need to. In fact, it's more hazardous, yeah, during deployment than when it's in place mining. Conclusions. Deep sea mining technological challenges are formidable. I only touch on the surface, in the previous slides. There are a lot more to how I have simply put them. We need to learn from trials. It's very important to do it step by step. And trials don't need to be successful. It is sometimes the mistakes or the unsuccessful trials that allow us to learn the most. Yeah. So we should do trials from 50 meters, 200 meters, 1,000 meters before we get to the 5,000 meter water depth. Let's not try to jump the gun too fast. Yeah. And the VTS, I believe, yeah, the vertical transport system raises the biggest concern, because we are toying between flexible TCP, lightweight, yeah, and then steel, and steel pipe is very heavy. You need big deployment facility, but it's got fatigue problem. So we all like to use lighter riser, but then lighter riser is not there yet because we don't have the diameter. So really, we're not. We haven't come out with the best solution, yeah, so to speak. Now, of course, the economical viability of a project relies heavily on the right equipment and logistics. I don't think we are quite there yet. You'll be a few years before we have the product, we have the technology that is ready, for commercialization. That's my presentation. Thanks very much for your attention.
Thank you so much, Frank. We are going to take some questions. I've already had quite a few come in, and we're trying a new thing today. Hopefully you guys can see it. I added a little poll. If you'll just let us know how the content kind of met your expectations today, that would be really helpful. So I'll leave that up there while we do some questions. Okay, let's see. First question. Um, does 2H own all of the seafloor crawler and recovery assets? Yeah.
Can you repeat that? Does
Does
2H
2H
what?
own all of the seafloor crawler and recovery assets?
No. 2H is a design engineering company. We don't own assets. We advise the stakeholders. This would be the contractors, the ISA contractors who have been licensed to explore and exploit the minerals. Yeah, we would help these contractors or the operators to advise them on the best system that they could have. They will have to, with our help, with our specification, go and buy and own those assets. Yeah. Now there are there are many operators, people who hold the licenses, but they are not all going to do to design the equipment independently. Yeah? So there are a number of companies who are offering these assets to the operators. You have a company like IHC, a company like GSR, which is a subsidiary of DEMI, and even OCs. Yeah, so they are investing into the equipment, the assets, ready to serve the industry. Yeah, but as 2H, we don't own the assets, any of the assets that you saw in today's presentation.
Okay, great. The next question is, for the pump option, are there no airlift options available? And would there be a potential for that, if not?
That's a good question, because I like airlift because you just inject air into the flow stream and then lighten it. You lift the slurry, yeah, the ore. Now, but here we are talking about very deep water depth, yeah? And I don't think anyone have done enough work to prove that airlift will work in such water depth. Airlift has been used in maybe 200 meters, max, and shown to be relatively efficient compared to the other pump options. Yeah, but because it's in shallower water depth. In 5,000 meters, can you imagine the bubbles growing in size because of the drop in pressure as you go up? The bubbles get bigger and bigger. So how efficient it is, because maybe the pipe inner diameter is all occupied by bubbles and not enough water to bring the solid up. Yeah? And so I like to believe that it can work. Yeah? I like to believe that it can work. But without more people researching into it and investing in trials, yeah, it's hard to prove this could work. And yeah, just that the behavior of bubbles, going up the pipe gets bigger and bigger, and there's a cooling effect there, Joule-Thomson effect associated with it. And yeah, I like to see that to be a good, viable option, but it's not proven yet. Yeah, for this water depth.
Okay, thank you. The next question, I think this was from the end of the presentation. It says, is there a flex joint at the upper end, and how long does the riser remain deployed without retrieval?
The top of the riser, I would suggest it to be either a flex joint, yeah, so that it is not a fixed end boundary condition that would have a very high bending moment and bending stress. A flex joint or gimbal, yeah, will negate, yeah, or reduce the bending stresses there. But it depends on the axial resonance, yeah, behavior again. If axial resonance is an issue, then a flex joint or gimbal alone does not solve your problem. Yeah, you need to have a soft hang off, not a hard hang off. Yeah, so you could be a compensator. Yeah, you need a compensator to hang this top end of the riser on, together with a gimbal, yeah, that allow some rotational freedom. So that will remove some axial resonance problem and reduce your bending stress. Yeah. So that needs to be a careful design, a compensated design, compensated and angularly free design. Yes. And how long can we leave this riser in the water? So, right, we would like to leave it in the water as long as we would like to, and never have to retrieve it. But I think that's why we're wanting to look at pipe material that is fatigue resistance. Yeah, a steel riser pipe, if especially when you have VIV, then you would have fatigue and you will have limitation on how long you can stay in the water. I would like to say that we can leave it now for at least 6 months before I feel that this is a good, robust system, yeah? And or maybe even longer. Yeah? And with careful monitoring, design is one thing. You can do a lot of design calculations, assuming the environment, and then we would always design it conservatively. But then I would say when we deploy a commercial system, we need to have a monitoring system in it to actually know what is experiencing, and then make operational decision from the monitored data to leave it in water for as long as we can.
Okay, great. Moving on to the next one. At what stage are the environmental studies at what stage do the environmental studies happen in relation to the effects of seabed mining? Are these at very deep depths? Does that make sense?
In fact, this is everyone's concern about the environmental impact of deep sea mining, and I'm not qualified or equipped to comment on it, but I can say to you that I say, under pressure from all the environmental group, take this extremely seriously. Yeah? So when they issue the licenses, yeah, the applicants, or before they issue the licenses, the applicants have to come up with all sorts of environmental impact statements, assurance that they will safeguard the environment, in fact, there have been a number of GIPs. We took part in the Blue Knot Mining GIP. It was European Union GIP that lasted for 4 years, which ended 2 years ago, and then it was followed on by Blue Nodule GIP, also European Union. We are not part of it, but the The blue mining concerns the vertical transport system and the vessel, production vessel, and the general economic and economic appraisal of seabed mining. The technology readiness levels of the main components. Blue nodules, the one that follow it, focus on the crawlers, what happened on the seabed, and a lot of effort was spent on the plume study, suppression of plume, the how we could minimize the impact. It's important to say that everybody takes this environmental impact very seriously, and you need the expert companies, technologically advanced company like 2H, for example, to be involved, and design the right equipment to do it, without failure.
Okay, we're going to squeeze in one more question. Would an existing conventional drilling riser, which might be available at a cost discount, be an attractive solution?
It would be, but it's too big, too heavy, because the conventional drilling riser is 21 inch, so it's quite a large diameter, and we have only, for mining, we need around 14 inch ID, internal diameter, 12 inch, 14 inch, that kind of range. But 21 inch is more than enough for us. The other thing to remember is that, larger diameter doesn't mean that you could, it's more efficient. You can bring more things up, because a lot depends on the flow velocity, the transportation of the ore up the riser depends on the flow speed. You need flow speed of something like at least 4 to 5 meters per second to transport the ore efficiently. Now imagine you have a larger internal diameter, then you need an enormous pump, to pump a lot of flow to reach that speed. Okay, you may argue that you could reduce the diameter of the drilling riser, put a hose or something like that, inside the drilling riser. You can, but still your external casing, which is the 21 inch drilling riser, is still formidably heavy, in 5,000 meter water depth. Now in 2,000 meters, it's a different story. 2,000 meters, then I think it's quite doable, because most drilling risers, in fact, the modern drilling risers are designed for 3,000 meter water depth. So up to 3,000, an existing drilling riser can do the job. But you need about the flow speed I was talking about. You need to put a smaller pipe inside the 21 inch drilling riser. Yes, it's possible.
Okay, great. Well, thank you so much, Frank, for all the information on the topic. That's all the time that we have for today. But as we mentioned earlier, if we didn't get to your question, or if you'd like to continue this discussion, you can contact Frank using the details provided here. Thank you all to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening every 2 weeks during our time at home. Our next webinar will take place on October 7th with the topic of flexible pipe reuse. You can check out the 2H website or LinkedIn to sign up. And again, please look out for the recording of the webinar in your email in the next 24 hours. And we hope everyone enjoys the rest of their day. And thank you.